Hi guys, thanks for tuning in. In this video, I'm going to talk about Lagrange multipliers. This is a technique of constrained optimization. So for this particular video, I have a function f of xy that I want to find the extrema of subject to a constraint g of xy is equal to 1. Basically, I have a function z equals f of xy that I want to maximize or minimize subject to this constraint. This sounds a little bit abstract, but if you think about your z equals f of xy as a mountain, as a surface living in three-dimensional space, and you think of your g of xy equals 1 as a hiking trail that you can map onto that mountain, all I'm really trying to do is find the points on our hiking trail at the highest and lowest altitude, the highest and lowest z value on that hiking trail. So let me try to get a visual for you to make this a little more concrete. So I'm going to start by plotting my z equals f of xy. So I have some fairly complicated equation here, and it plots out as this surface. Now, this is a constrained optimization problem, so I'm not looking for the top and bottom of this mountain necessarily. Instead, I need to map a hiking trail onto this mountain, and I'm looking for the highest and lowest points on that hiking trail. So let's build up our hiking trail and get it onto this mountain. So my constraint is my hiking trail. I have g of xy is equal to 1, which is a curve that lives in two-dimensional space. A plot of this curve is two-dimensional, so here it is. You can see that it's just a standard ellipse. Now the good news is I actually know how to parameterize an ellipse. So for this particular problem, I'm going to leverage that ability and use that to plot this hiking trail on my mountain. Now this is not something that's always easy to do. For a general curve, coming up with a parameterization is not necessarily an easy task to complete. But for an ellipse, it's not so bad. So I'm going to come up with some x of t, y of t describing this ellipse. It's 3 cosine t, comma 2 sine t plus negative 3, comma negative 2. This parameterization is equivalent to my ellipse. And then I can map this curve onto my mountain. I can get my hiking trail by plotting x of t, comma y of t, comma f of x of t, y of t. So here it is. I've got my surface and my hiking trail together. And as a constrained optimization problem, I care about the points on this hiking trail that have the highest and lowest z values. That's what I mean by constrained optimization. I'm not looking for the top of the green mountain or the bottom of the green mountain. I'm looking for the highest and lowest points on this red hiking trail. Now if I zoom in a little bit closer, you can kind of spot it. It looks like I have a highest point and a lowest point. I have a maximum and I have a minimum, but there's a couple other points that are interesting, right? Looks like I have a little local maximum here, a little local minimum. Let's try to figure out how to pinpoint all of these candidates and then talk about how to figure out which of these candidates correspond with the global maximum and the global minimum on this curve. So let's think back to our previous calculus course. This is a curve. And a curve is going to rely on some of the intuition that you guys came into this course with. You already knew how to find candidates for maxes and mins on curves. Basically, the places where you have a horizontal tangent line. More specifically, the places where df dt is equal to 0, or df dt changes from positive to negative or from negative to positive. Those are going to be our candidates. So let me add a tangent line to our picture here. And we can kind of drag the slider and we could see our candidates. You could see that as this curve changes from decreasing to increasing, somewhere in between I must have had a place where I had a horizontal tangent line, a place where df dt is equal to 0. That's what I'm trying to pinpoint, the places where df dt is equal to 0, the places where this tangent line goes from either increasing to decreasing or from decreasing to increasing. And in between those changes, we have a place where df dt is equal to 0. We could see that it looks like we have 4 candidates, 4 places where we have a horizontal tangent line. And those 4 locations for our 4 horizontal tangent lines are going to be our candidates for maxes and mins, for global maxes, well, local maxes and mins, but ultimately a global max and a global min. So I did some computation ahead of time and I found out where these candidates are. I used the methods that I'm about to teach you to find the answer to this problem. So let me plot these, and that'll give us just a slightly better visual where we could see, oh yeah, looks like we've got a candidate here. The curve changes from decreasing to increasing, so somewhere in between we must have had a location where df dt was equal to 0, a location where we have a horizontal tangent line. And we have 1, 2, 3, 4 of those candidates. Let's figure out a method for honing in on those candidates. So again, we're looking for the places where df dt is equal to 0. And I'll be honest, if we're lucky enough to be able to parameterize our constraint curve, there is a way of doing this problem using only knowledge that you guys had from last year's course, which is you could parameterize your curve, plug x of t, y of t into our function f, and then solve the equation where this derivative is equal to 0, and those will be your candidates. But the reality here is curves of the form g of x, y equals a constant are oftentimes difficult to parameterize. They're not always ellipses and circles. Sometimes we have things that are difficult, if not impossible, to parameterize using the techniques that we already know. So we really want another technique that allows us to leave our curve in g of xy equals k form, in xy form. We don't want to have to parameterize. And honestly, three-dimensional plots are kind of hard to produce. So we also kind of want a method that allows us to think in two-dimensional space rather than always having to resort to where this problem actually lives, which is three-dimensional space. So we're going to try to come up with a technique that stays in two-dimensional space and allows us to keep our curve in xy form. All right, so let's develop that. So again, we're looking for the places where df dt is equal to 0. But we already know the chain rule. We know that df dt is equal to the gradient vector dot producted with the tangent vector. So now we have a slightly different condition here. If we could find the places where the gradient vector and the tangent vector have a dot product of 0, we have found our candidates. But remember that two vectors have a dot product of 0 if and only if they're perpendicular to each other. And also remember that the gradient vector and the tangent vector here live in two-dimensional space, which is kind of nice because now we're able to plot everything on a contour plot in two-dimensional space. So this picture right here, it's still our surface, but now represented as a contour plot, as a bunch of level curves. And we still have our hiking trail, our g of x, y is equal to 1 here. But now we have a two-dimensional representation of this whole thing. And we're looking specifically for the places where our candidates are going to be at the places where our two vectors are perpendicular to each other, where the tangent vector and the gradient vector for f are perpendicular to each other. And you can still see we have 1, 2, 3, 4 candidates. Those are the same candidates that we saw in the three-dimensional plot. But now we're representing this in two-dimensional space, and we've made it a problem of vectors instead of a problem about where df dt is equal to 0. But they're equivalent because of the chain rule. Now there's an interesting thing here. Look at how our candidates are at precisely the places where our level curve and our constraint curve, our hiking trail, are tangent to each other. Now that's not by accident. That actually is an interesting phenomenon. We're going to see that develop as we go through the rest of this video. You'll see why that's the case. But again, we could see our 4 candidates in this graphical representation here. Now I did try to make it a little bit easier to switch between candidates. So here's a slightly updated plot where I can click some buttons and see where my 4 candidates are. The places where the gradient vector and the tangent vector are perpendicular are the places where df dt is equal to 0, which are our candidates for the highest or lowest points on this hiking trail on this mountain. Now, the next leap we have to make is, remember we had this curve x over 3, or x plus 3 over 3 squared plus y plus 2 over 2 squared equals 1. That was some g of xy is equal to 1. Well, we can think of that as a level curve to some equation g of xy. And the reason that we would want to do that is we know that gradient vectors are perpendicular to level curves. So this is a clever way for us to get some normal vectors to this ellipse. So the gradient of g, that is going to give us vectors that are perpendicular to this red ellipse. So I'm going to go ahead and plot them. Looks like the same visualization we had before. The only thing that I've added are these orange vectors, which are the gradient of g. G of xy is equal to 1. They're basically just normal vectors to our red curve here. And what you'll notice is at our candidates, you either can look for the places where the gradient vector, the blue gradient vector here, the gradient of f, is perpendicular to our tangent vector. Or you could look for the places where the gradient to g and the gradient to f are pointing in the same direction, right? You're not at a candidate when they're pointing in different directions, and there's not a right angle between the tangent vector and the gradient of f, but you are at a candidate when your two gradient vectors are parallel to each other, and there's a 90-degree angle between the tangent vector to the ellipse and the gradient of f. So let's try to work with that information. So here's just an algebraic summary of what I just said. We either want the places where the gradient of f and the tangent vector to the ellipse have a dot product of 0, where they're at a 90-degree angle with each other, or equivalently, we want the places where the gradient of f and the gradient of g are parallel to each other. Well, two vectors are parallel if they are scalar, non-zero scalar multiples of each other. So if we have the gradient of f is equal to s times the gradient of g, this condition will be equivalent to the previous one about the right angle between the tangent vector and the gradient of f. All right, so let's use that to simplify our picture a bit. So we are specifically looking for the points at which the gradient of f, the blue vector, is parallel to the gradient of g, the orange vector here. These are our four candidates, and we could see at the other points these are not candidates because they're not parallel there. And there is one other condition, which is we only care about the candidates where these are multiples of each other, they're parallel to each other, and their tails are on the ellipse itself. So we have one other condition here. We do have to satisfy g of xy is equal to 1. We have to be on the red curve to care about the times at which this happens. All right, so we did it actually. This is the method of Lagrange multipliers. This is constrained optimization using Lagrange multipliers. What can we do with this realization that we're solving a system gradient of f equals a multiple of the gradient of g? Well, we could try to find the extrema of some surface, z equals f of xy, subject to some constraint, g of xy is equal to a constant, by solving this system of equations such that this system of equations satisfies the original constraint, g of xy is equal to 1. So what we've done here is basically we're finding candidates for the highest and lowest points on a hiking trail on a mountain, as long as we're on that hiking trail, and as long as we are representing our hiking trail as some g of xy is equal to a constant. It's pretty cool because we don't need to parameterize our g of xy equals a constant. We don't have to parameterize our constraint. And on top of that, we're also lucky enough that this entire calculation is happening in two-dimensional space. This is a two-dimensional vector here, right? Or this is a two-dimensional vector on the left side set equal to a scalar multiple of a two-dimensional vector on the right side. And then we could turn that into a system of equations and solve. Mathematica is really quick. We could put Mathematica to work on a system of equations like this, and it'll spit out answers in just a couple seconds. And we could plug those answers into points on our hiking trail, and we're going to get our four candidates. So here they are. These are our four candidates for our global extrema on this closed curve. Now, they're all interesting points. They're all local maxes and mins, right? We have a local max right here. We have to compare and see if the one on the left or the one on the right here is the global minimum, but we know that at least they're local minimums. And then same thing here. This looks to me like it's going to be our global maximum. So anyway, we have four candidates. We need to figure out which ones are our global extremes. And we do it the same way we would have done this in Calc BC. We just compare all of our candidates essentially in a table here. So I'm just having Mathematica print out my four candidates. I'm going to look at these z coordinates. And I want the points that have the highest z coordinate and the lowest z coordinate. So my global max is 7-ish at the point negative 1.2 comma negative 3.6. And my global min, if I look through here, my smallest value is 3.21. So I have a global min of 3.21 at these coordinates. So I could plot it again. Here's a picture just with my global minimum and my global maximum. I have found the global extrema of f of xy subject to the constraint g of xy is equal to 1. Constrained optimization. Now I want to do one more problem, but I want to do this by hand because these are the sorts of problems that you get a better handle on the algebra if you do all of the algebra yourself rather than having Mathematica do the algebra. So it's a simpler scenario. It says find the extrema of f of xy equals 7x plus y subject to the constraint g of xy equals an equation for an ellipse. So I have a plane and I have an ellipse. So what you're imagining is you have an elliptical shaped hiking trail that's mapped onto a plane, and you want to find out what are the points at which I have a global maximum on this hiking trail, the highest altitude I achieve on this hiking trail, and where do I have a global minimum on this hiking trail? What is the lowest altitude I can manage to achieve while I'm walking specifically on this hiking trail? Well, the rest of this is really just algebraic. So I compute the gradient vector for both f and g. So the partial derivative of 7x plus y with respect to x is 7. The derivative of that with respect to y is 1. Similar idea for taking the gradient of g. We take the partial derivatives of this equation with respect to x, we get 2x, and with respect to y, we get y over 8. And now we set up our system of equations. So we set up that the gradient of f is equal to a multiple of the gradient of g. Remember, this is just like the little demonstration that I showed you guys above. We're specifically looking for candidates where these gradient vectors are parallel to each other. So we're trying to hone in on the candidates where we are locked in at parallel gradient vectors. Those are going to be our candidates. So let's go ahead and do it. So if we thread out this system, if we take out the x coordinates, we get 7 equals 2sx. If we take out the y coordinates of this equation, we get 1 equals sy over 8. And then what you don't want to forget is that the constraint is also part of your system of equations. We only care about this condition being satisfied for points that are on our curve. We only care about the points that are on the hiking trail. So this is part of your system of equations, which is a good thing because if you look here, we have 3 equations and 3 unknowns. And so we've got a pretty good shot of solving this by hand. So I'm going to go ahead and solve both of my first 2 equations for s. Now, if these 2 equations both equal s, then they both equal each other. And then I'll solve for y. I get y equals 16 over 7 times x. Now, I can take this result and plug it into my constraint, and I could try to figure out where my candidates are. So I'm going to take 16 over 7 times x, plug it into the equation for the ellipse, go ahead and do some simplification, and then I get x is equal to plus or minus 7 over root 65. So I know I have a candidate at positive, and an x value of positive 7 over root 65, and another candidate at x equals negative 7 over root 65. We're going to plug both of these in to our y equals equation, and then we're going to get y equals positive 16 over root 65 and y equals negative 16 over root 65. Now those are our 2 candidates. To figure out where we have a global max and a global min, I have to plug these candidates into f of xy is equal to 7x plus y. This is the function that we're trying to maximize or minimize subject to our constraint. So this is the value that we care about for maximizing and minimizing purposes. And you're going to get z equals root 65 for our global maximum, and z equals negative root 65 for our global minimum. Mathematica can solve this in like a tenth of a second. So here's just showing you how quickly Mathematica can knock out a system of equations like this. And finally, just to make it visual, again, what were we doing geographically, or geometrically, what are we thinking about here? I guess geographically as well, if we're thinking about this as a mountain. But we're hiking on this hiking trail, and we care about what is the highest altitude that we're able to achieve, and what is the lowest altitude we're able to achieve when we're limited to walking on this hiking trail. We found the global extrema of f of xy subject to the constraint g of xy is equal to a constant, where in this case g of xy was equal to the constant of 1. Now what's really neat about this technique is I think it's great when we can make everything graphical and really give you some geometric interpretation of what we're doing here. But this optimization technique is not limited to things that you can picture in your head. So we could do some pretty cool problems in engineering and economics and some other fields as well, some other optimization problems where we don't really have a surface and a hiking trail visualized in our head, because this algebraic technique will extend to as many dimensions as we'd like. So here's an example that we're not going to be able to plot. We have a cargo container in the shape of a rectangular solid. Now we have a fixed volume. This cargo container needs to fit exactly 480 cubic feet of cargo. But the thing that can vary are the exact dimensions of this rectangular solid. And we want to pick the length and width and height of this rectangular solid so that we've minimized the cost of building the shipping container. Now, we're told that the bottom of the shipping container is $5 per square foot to construct, while the sides and the top of the shipping container are only $3 per square foot to construct. A little bit of suspension of disbelief here. We don't know exactly why those cost differences exist. Maybe it's something that, like, the bottom of the shipping container has to be thicker or more or higher quality metal to make it a little bit stronger or something. Or maybe it's made out of a different material on the ground. Who knows? But suspension of disbelief, let's pretend that the base of this rectangular solid is more expensive and the walls and ceiling of the shipping container are less expensive to construct. And we want to find the dimensions of the container that minimize the cost of building it. So you can kind of see the connection here to economics, to business, and to engineering. And by the way, I didn't write this problem myself. This is from the Larson and Edwards multivariable calculus text, the 10th edition. So you can easily find this problem if you wanna see the source there. Anyway, the hardest part of these word problems is coming up with the setup here. So we need an equation that we are maximizing or minimizing, and we need an equation that serves as our constraint. But what's pretty straightforward here is that our constraint is that we have to have a volume of 480 square feet or cubic feet. So g of x, y, z is equal to the volume here, so length times width times height, which is locked in at 480 cubic feet. That's my constraint. That's my g of x, y, z. Now the function that I'm optimizing, maximizing or minimizing, is f of x, y equals, this is the cost of building the shipping container. What you can see is it's $5 per square foot for the base, so length times width, and then everything else is $3 per square foot. So we have the ceiling, x times y, length times width. We have the two walls, or actually the four walls. Two walls are constructed out of a length and a height, and two walls are constructed out of a width and a height. And when you multiply this whole thing out, you get this 8xy plus 6xz plus 6yz. Well, once we have our setup, Mathematica can solve this very, very quickly. So plug in your equations. Tell Mathematica what it's solving. It's just a system of equations here. The gradient of f is equal to a multiple of the gradient of g, plus our constraint curve is also part of our system. And then Mathematica is going to solve for 4 equations with 4 unknowns over the set of real numbers. And look what we get. We have our dimensions. The container should be about 7 feet by 7 feet by 9.5 feet, and it's going to cost us about $1,200 to produce. Thanks so much, guys, for tuning in, and I hope you enjoyed this video about Lagrange multipliers.